Now we're going to begin the last podcast for this chapter, even though it's about solutions, talking about things that aren't solutions, and specifically heterogeneous mixtures. Now there's a few of them, and the first one's very easy to understand. It's called a suspension. Remember, these are not solutions. Hetero means different. A solution is a homogeneous mixture. These two types of mixtures we're going to discuss right now are heterogeneous. You can see the different layers in them. So it's a mixture that contains particles that will stay thoroughly mixed as long as you keep stirring them, but they settle out when left undisturbed. So let's look at an example of one that's a pretty obvious suspension. Cars keep going through the muddy puddle, or people keep tracking through it. The mud particles stay suspended in the water. But if you take a sample of that, as you can see on the right-hand side, and let that muddy water settle out, then you know that you had particles that were so big that they never dissolved. They were just sort of hanging suspended, and then they settled out over time by the forces of gravity. Chocolate milk falling down to the bottom of your glass if you made it with powdered milk and you let it set for a while. Or if for some reason, as shown on the bottom right, you decide to mix some chalk with water, the little bottle with the blue cap shows the suspension. The test tube on the left shows over time how the suspended water, or the chalk molecules in the water, will settle out. Now, colloids are also not a solution, but they're little odd kind of ducks, and yet they're very important biologically. Colloids, or colloidal dispersions, are kind of a suspension, but the particles are bigger than molecules, but they don't settle out. So they don't go into solution and dissolve. They're too big for that. But they're too small, though, to have separation by the forces of gravity. Now, it has a range here of 10 to 2,000 angstroms, but I think if you see some examples of colloids, you'll understand what we're talking about. Let's take fog, for example. The colloid phase would be gas, and the thing that's dispersing is the solvent, so that's where the solvent like comes from. And the thing that's getting dispersed is the solute-like. So when tiny particles of water are dispersed into the air, that would be liquid and air, and they don't settle out, that's fog. And you know this will be a colloid, as you'll see in just a moment. Those of you who've driven in heavy fog, when you see the beams of your light from the headlamps shine through the fog, you're observing something that proves you have a colloid. The particles of suspended foggy water scatter or disperse the headlamps, and you can actually see the beam of your headlights in the fog. You can't see that on a non-foggy night. Another interesting, tasty one would be the phase of the colloid is solid, and the thing that is acting as a dispersing agent is a solid, and when you put little pieces of gas in it, you've got yourself what we call a solid foam, or also known as a tasty marshmallow. Probably 99% high fructose corn syrup. But a solid foam has the dispersed solute-like substance as the gas, and the thing that it's dispersed in, kind of like a solvent, is a solid. So there's some other examples there, such as whipped cream. That's a gas being dispersed in a liquid. That's a foam. I'm not sure what a sol is, so I'm not too worried about that. But let's go on and look at some more examples here. Paint is a liquid and a solid. We already talked about marshmallows. When you buy homogenized milk, that's a liquid dispersed in another liquid. That's milk. It has fat particles and proteins that get dispersed in the liquid water part of milk. We talked about fog and smoke. So there's a number of examples of what colloids are. Remember that their particles are smaller than those in suspension, so they don't settle down due to gravity, but they're larger than those in homogeneous solutions. Here are some models of colloids and suspensions. There's a foggy day, and here's another one, aerosol shaving cream. So how do you know that you have a colloid? This factor is called, or the effect is called, the Tyndall effect. You've actually seen it if you've ever looked at a beautiful sunrise or sunset on a day that's quite smoggy, or perhaps has a forest fire going on and in the atmosphere there's a lot of particulate matter. So the colloid particles are large enough to scatter light, and if you shine a beam of light through a colloid, you can see the pathway of the light. When you look at the beautiful red sunsets or sunrises on a smoggy or smoky day, you see mostly reds and oranges. That's because as you look at the rising sun through all this junk that's in the air, the red and the orange wavelengths of light are scattered more than the blue wavelengths. And so that's what gives the beautiful colors. It also gives kind of, if you've been near a forest fire and when you look down at the ground and you look at your shadow, there's sort of an orange hue to everything. That's also the Tyndall effect. Now, what can happen with colloids, though, is that there are things like proteins that you've got to figure out a way to have it stay dispersed in your bodily fluids. And you probably know that hydrophobic, phobic means you're afraid of something, and hydro stands for water. Well, you can categorize some of these colloids as water-loving or water-fearing. So the water-loving colloids are called hydrophilic. That's what the Latin root is for liking something. So in the human body, what you can do with these big proteins molecules is you can fold them up in such a way that you keep the parts that are afraid of water in the middle, and you take the parts that like water, the hydrophilic parts, on the outer edge, and they can interact with the water molecules. Here's a picture of that. Notice that they put in white the parts of this big giant protein that are afraid of water, but on the edges are things like oxygen atoms that have plus charges. That's probably like a nitrogen group over here in the end that's got a plus charge. Yeah, there it is. So these groups on the outer edges, they have charges on it, and because they're charged, they're going to be attracted to those partial positive and negative charges on the polar water molecules. So it stays mixed in. It becomes a colloid because it kept the water-fearing parts of the big protein in the middle. Now, you and I use soaps a lot. And you know that if you drop a drop of oil in water, you're not going to get oil and water to mix unless you add something called a surfactant, and in this particular case, a soap. A soap is a molecule that has a long hydrophobic tail. So it's kind of misspelled here, hydrophobic. Here's the long tail that's afraid of water. But then it has a part that has a charge on it that's water-loving. And so what can happen is that the head of the soap, the hydrophilic part, will dissolve into the water. So here's an example. A lot of soaps have sulfates on the end. And when you see a long bent chain like that, that's a chain of carbons. And they're the part that have no charge, don't dissolve in water, are afraid of it. The sulfate or phosphate groups on the end, they do have a charge. And so what it acts like, the soap does, is it kind of joins together two things, an oil droplet and a water molecule that normally wouldn't mix. The charged end is attracted to the charged parts of the water. The uncharged or nonpolar end will dissolve into the oil droplet. And so you mix the soap with the water, wash off the oily grease on your hand, and it rinses away. So most dirt stains on people and on clothing are oil-based. Now here's kind of an interesting little animation. It'll take a moment here to boot up. It talks about how you can take a molecule of fat or oil that has 3 free-swinging glycerin groups here. So you put in some sodium hydroxide, and then they join up and create soap through a process called saponification. And soaps, as you can see, have a fat-loving end and a water-loving end. So when they made soap in ancient times, you would need a source of sodium hydroxide, which is lye. You would need animal fats, and you can also mix in ash from fires to make soap kind of the original old-fashioned way. How somebody found that out, I have no idea. Finally, when you digest fats, you have your stomach laying off of it, your little gallbladder, and your gallbladder excretes a substance called bile. And bile salts that come out of this gallbladder, they make an emulsion with fats in our small intestines so that they can be absorbed. So there's a lot of biological applications of this principle. Finally, here's a digestive example. When you make homemade salad dressing, it looks like the one on the left or on the right. You can see here in the center someone's put some balsamic vinegar in with some probably olive oil and some sprigs of rosemary, but nothing's dissolving. Oil and vinegar are not going to mix. What you need to add is a substance called an emulsifying agent, and the example is lecithin. And just like the soap, the lecithin has a part on it that's nonpolar that will dissolve into the olive oil, and it has a part on it that's polar, and that's the part that will dissolve in the polar acetic acid or vinegar. So when you purchase a store-bought salad dressing, which has lecithin or some kind of emulsifying agent added to it, you get a salad dressing that looks like here on the right-hand side. Stays all mixed together because they've added an emulsifying agent. That concludes our PowerPoint, and I believe the 4th vodcast on the series for the solution chapter. Until next time.